Hi, in this talk, I represent our work gradient regularized relearning for dynamic treatment regimes. A dynamic treatment regime is a sequence of decision rules that determines which treatment to give to the patient at each time step. For examples, at time t, we want to learn the optimum decision rule for assigning radiotherapies and chemotherapy to cancer patients. In the figures, the left panel shows that if we do not assign any treatments at time t, the tumor volumes will go up. If we use radiotherapy, the tumor volumes will go down slightly. The most effective treatments at time t is chemotherapy, which will cause the tumor volume to drop significantly in the future. In the dynamic treatment regime, we want to learn the decision rule that select the best treatments at each time step. Besides treatment recommendation in perceptual medicine, there are other applications of DTRs. For example, recommend product to customers in recommended system. If we move from the time domain to spatial domain, we can use DTR to decide how to launch social policies over a country. Suppose we have a dataset with n individuals and t time steps. Each individual in the dataset has a baseline covariate vector z, also denoted by h0. This vector stores the static information about the individual, such as age and gender. At each time step, the individual has a covariate vectors xt, a treatment variable at, and an outcome variable yt. We denote history up to time t by ht. Ht includes all the covariates and treatment variables up to time t. We denote the history up to time t without the treatment variable at time t by h tilde. The assumed data distribution starts with the initial distribution p h0. At each time t, the covariate xt is generated by the histories up to time t minus 1. The treatment variable at is assigned based on history h tilde. The outcome yt is generated by the history ht. Given the history h tilde, the time t treatment rule dt is a function that assigns the treatment variable at based on the history h tilde. A dynamic treatment regime is simply the collection of the treatment rule over all the time steps. We want to find the treatment rules or DDRs that maximize the outcome accumulated over time in expectation. The expected accumulated outcomes over time is often called as the value function. We denote the time t value functions by Vt. It is the expected accumulated outcomes by following the treatment rules added after time t. The value function under the DDR is the time one value function, denoted by Vd. It is the expected accumulated outcomes by following the treatment rules in the entire treatment trajectory. The optimum DTR is often defined as the DTRs that maximize the Vd. To optimize the DTR, we will need to estimate the value functions Vd. There are a few general challenges in value function estimation and DTR learning. First, we cannot experiment treatments to collect more data. Even the dataset we have is large, the signal of the positive outcome may only realize after a long period of time. In this case, the uncertainty of the future outcomes could be very high. We will need to introduce multiple machine learning models to estimate the outcomes and treatment assignments over time. It is hard to manage the model not to overfit to the data. The value function's estimation is often biased by the observed data and sensitive to the performance of the used machine learning models. To estimate the time t value function, we will need to estimate the long-term expectation of the outcome yr. R is larger than t. The expectation of yr is estimated by applying sequential regression backwardly starting from time r. At time r, we estimate the expectation of yr given histories up to time r. And by the law of iterated expectations, we compute μs by estimating expectations of μs plus 1s given histories up to time s. In practice, μs is computed by regressing μs plus 1s onto the histories hs. After r minus t's regressions, we will obtain the wanted expectation of YRs given histories up to time t. To understand the bias in computing expectation, we rely on the several parametric theories in statistics. We view the value function estimators as the functional size that apply to the ML model that estimates the outcome and treatment assignments at and after time t. Under some regularity assumptions, the value function estimators admits the Fourier's expansion. Roughly speaking, Taylor expansion of functional. The first order bias of the estimator is given as the sample average Pn of the efficient inference function dt star. These expansions motivates a class of debiased methods by solving the estimating equation, which sets the sample average dt star to 0. Example for this includes doubly robust estimators and one-step estimators. These methods try to correct the first order bias after the model is trained. first order bias correction method may not be effective given some poor machine learning models in modeling the outcome and treatment assignment. An analogy question for this is to think about whether the first order Taylor expansion of a function is always a good approximation of the function. Here is a one-dimensional example of how one-step estimators works in estimating the expectation of the square density. The true expectation is shown in the blue circle. Given a poor density estimate, the one-step corrections may send the estimator to the wrong place. In general, like approximating a function with its first-order Taylor expansion, the first-order bias correction methods prefer the curvature of the functional to be flat and a good initial machine learning model, so that the first-order derivative can approximate well the local change of the function. In our work, instead of correcting the bias after the model is trained, we regularize the model to solve the estimating equations in training time. It is an extension of the target regularization methods for arbitrary estimation. In value function estimation, we propose a new regularizer to solve the complex estimating equation, which involves the model to estimate the long-term expectation at multiple time steps. The IM model we use is shown in the figure. We use an encoder to encode the histories up to time t's into a representation. On the representation, we use a decoder mu to estimate all the future outcomes and use a feedforward network G to model the treatment assignments at time t. We call the network G as the propensity score model. We train our IM with the regularizers RT. The regularizers RTs can be written as a sum of zeta function. Zeta R is simply the MSE of predicting the outcomes at time R. Zeta SR is trying to match mu S, the expectation given history is up to time S, and mu S plus 1, the expectation given history is up to time S plus 1. Note that mu S in the zeta functions are perturbed by FNTs times the propensity score model. We prove that when the regularizer is minimized in model training, the derivative of the regularizer with respect to epsilon t is equal to 0. Then sample R with dt stars is also equal to 0. Finally, in experiments, we apply our method to value function estimation and DTR learning. We include application examples such as treatment cost trade-off and survival rate maximization. Our method GRV estimates the value functions more accurately and learn a better DTR to maximize the true value function compared with the benchmark methods. Thank you for watching. If you're interested, take a look at our paper and softwares on our website.